Hello students, as we discussed nucleophilic substitution reaction and its mechanism, let us discuss stereochemical aspects of nucleophilic substitution reaction. The stereochemistry plays a significant role in the nucleophilic substitution reactions. So in order to explain the stereochemistry of nucleophilic substitution reaction, first of all we need to discuss some of the terms which we'll be using in this. So let us discuss the terms. First one, plane of polarized light. What is this plane of polarized light? As you're familiar with the normal light, a beam of ordinary light which consists of electromagnetic waves vibrating in all the planes in the space, as it is shown in the figure here. When the ordinary light is made to pass through a nickel prism, which is a type of polarizer here, it is observed that in the prism the vibration in all the other plane except one are cut off. So we'll get that light is called as plane of polarized light. Here nickel prism, which is act as polarizer, is a special type of prism made of crystalline calcium carbonate, which act as a polarizer which makes the normal light into plane of polarized light. So when you check the structures here, in the normal light you can find that electromagnetic waves vibrating in all the planes in the space, but in the case of plane of polarized light you can find that all the vibrations are cut off except one is left. This is called as plane of polarized light. When the plane of polarized light is made to pass through a substance, this substance can be a solution of any of the organic compound. So when it is made to pass through a substance and when it is analyzed through an analyzer, if the plane of polarized light is rotated by certain angle either in the right side or in the left side, we can say either in the clockwise direction or in the anti-clockwise direction, then such substances are called as optically active substance. And the substance which does not rotate the plane of polarized light is called as optically inactive substance. So in this figure you can find that the plane of polarized light is rotated by an angle that is alpha. So we can say that the substance which is taken here in the sample tube, that is optically active. If the substance does not rotate the plane of polarized light, then it is called as optically inactive. This can be analyzed through an analyzer as shown in the figure. So what is optically active substance? The substance which can rotate plane of polarized light either in the clockwise direction or into the anti-clockwise direction is called as optically active substance. When the sample rotates the plane of polarized light in a clockwise direction, then such type of substance is called as dextra-rotatory substance or D form of substance. Such substance is represented by positive sign with the angle of rotation. Here, dextra word means a Greek word which means right rotating. That means it rotates the plane of polarized light in right side, that is clockwise. And when the plane of polarized light is made to pass through a sample, when it rotated by an angle alpha, that is on the anti-clockwise direction, then such type of substance is called as levorotatory or L form of substance. Here it is represented by negative sign with the angle of rotation. Here levo means left rotating, therefore it rotate in the left side, therefore it is called as levorotatory. Thus, we can say that when the ordinary light which is made to pass through a nickel prism, which get plane of polarized light and which is passed to a substance, that is a sample taken in the sample tube, then the plane of polarized light rotate by an angle called as alpha, and it is observed through an analyzer. So, the angle by which the plane of polarized get rotated can be measured with the help of an instrument called as polarimeter. Thus, a substance which rotates the plane of polarized light in any of the direction, either clockwise or anti-clockwise, such type of substance is called as optically active substance. And the substance which does not rotate the plane of polarized light, such type of substance is called as optically inactive substance. So we have classified the substance into two types. The substance which rotating the plane of polarized light is optically active, and which does not rotate the plane of polarized light is optically inactive substance. From this figure, it is clear that the substance rotated the plane of polarized light in a clockwise direction, that is this direction. Such type of optically active substance are called as dextrorotatory, and which can be represented by plus sign with the name of the substance, and it is observed through the analyzer. And when it rotates the plane of polarized light in anti-clockwise direction, then such type of optically substance are called as levorotatory, which can be represented by negative sign with the name of the substance, and it can be observed through the analyzer. So we can conclude the three type of substance which we have learned here. That is optically inactive substance. When there is no rotation, it is optically inactive. If it is a rotation in a clockwise direction, then it is dextrorotatory, and if there is a rotation in anti-clockwise direction, then it is levorotatory, or we can say negative charge is represented, or L sign is used for levorotatory, and D or positive sign is used for representing dextrorotatory. As you know that carbon is tetravalent, that means it have 4 valency, and the 4 valency can be satisfied by 4 atoms or group of atoms. So, if these atoms are different as shown in the figure here, it is shown by different colors. So, if these are of different groups or different atoms, then such type of carbon is called as asymmetric carbon. That means if all the atoms or groups attached to a carbon are different, then such carbon is called as asymmetric carbon, or we can call it as a stereo center. And such type of molecule is called as asymmetric molecule. That means a molecule containing asymmetric carbon would have lack of symmetry. Therefore, it is called as asymmetric molecule. Let us take one example. Look at this structure. Here, the star mark is made for the carbon atom, which is asymmetric carbon atom. When you find it out, the 1, 2, 3, 4, all the 4 groups here, or we can say here the 4 atoms are of different type. Therefore, such type of carbon which is bonded by 4 different atoms or group of atom is called as asymmetric carbon. Asymmetric carbon is represented by making a star on it as shown in the figure. Let us take one problem. Look at the two structures. These are the two organic compounds. Identify the asymmetric molecule from the following structures. The first structure, this is the carbon. When you find it out, the four groups surrounded by these, here there is one methyl group, this is also methyl group, one hydrogen and one hydroxy group. So from these, two are the similar one. You can find these two are similar. So asymmetric molecule means which have all the four groups or atoms different. But here two are similar. Therefore, we can say that this is not a asymmetric molecule. Let us take the next structure. Here, this is the carbon and which is surrounded by one ethyl group, methyl group, hydrogen and hydroxy group. From this, it is clear that all the four group or the atoms surrounding or which is called as bonded with the carbon is different. So, such type of carbon is called as asymmetric carbon and the molecule is called as asymmetric molecule. So, the second structure is asymmetric molecule, but first one is not a asymmetric. As asymmetry of the molecule is responsible for optical activity in compounds, the symmetry and asymmetry are also observed in many day-to-day objects. Let us discuss some of the objects. The most common example is our hand. If we hold your left hand in front of a mirror, then its image look like the right hand. If you try to superimpose left hand with the right hand, both the palms down, we observe that the hands cannot superimposed. So, such type of objects which is non-superimposable on its mirror image is called chiral. Let us take some more example. Look at this figure. Here, it is a bottle. When you find it out its image, it can be superimposed one on other. So, such type of object which is superimposable on its mirror image is called as a chiral. Let us find some more example. Here, some objects are taken and its mirror images is shown here. In the first series, we can find that object and its mirror images are superimposable. But in the second case, we can find that the object and its images are non-superimposable. So, the substance and its images is superimposable. Such substance is called as a chiral, and the substance which have non-superimposable mirror images are called as chiral. Similarly, we can observe the same in the case of molecules also. Let us take one molecule which have a asymmetric carbon, or we can say stereo center. When we observe its mirror image, it will be in this way. When you find out the object and its mirror image, these are non-superimposable. Thus, we can say that such molecules are chiral molecule. Let us take one particular example. In this example, you can find that the carbon atom is surrounded by 4 different atoms or group of atoms. So, this molecule is asymmetric molecule. But when we observe its mirror image, you can find that it is non-superimposable. You can see that the left and right hand side get changed here. It is non-superimposable mirror image. So such type of molecule which is non-superimposable on its mirror image is called as chiral molecule. and the non-superimposable mirror images are called as enantiomers. So these are the two enantiomers. The chirality in the organic compound was studied by Van 't Hoff and Liebel. He observed that most of the organic compound which are chiral in nature have at least one carbon atom which is bonded by four different atoms or group of atom. Thus, we can say that the molecule which is chiral molecule is due to the asymmetric carbon atom present in the molecule. Thus, we can say that chiral molecule is actually asymmetric molecule. Let us take one example. It is a asymmetric molecule because the carbon atom which is marked by star, that is asymmetric carbon atom which is surrounded by four different atoms or group of atoms. Such molecule is asymmetric molecule. When we observe its mirror image, we'll be getting the image in this way. From this we can say that the molecule and its mirror image are non-superimposable. Thus, the molecule is called as chiral molecule, and as studies observed that the chiral molecule shows optical activity, thus the molecule can be called as optically active, and the optical active molecules rotate the plane of polarized light. Therefore, we can say that asymmetric molecule having four different groups attached to the carbon, that molecule is asymmetric and which have non-superimposable mirror image. That molecule is called as chiral molecule, which is optically active and which rotate the plane of polarized light. Let us define a term, racemic mixture. An equimolar mixture of enantiomers, that is D and L form, is called racemic mixture. As shown in the figure, these are the D and L form. The mixture, that is equimolar mixture of these are called as racemic mixture because the D form is optically active, L form is optically active, but their mixture, that is DL form, is optically inactive because D form rotate the plane of polarized light in clockwise direction and L form rotate the plane of polarized light in anti-clockwise direction and in the same magnitude but in the opposite direction. Thus, the net rotation will not be there. Thus, it is optically inactive. Here, the process of converting D and L form into DL, that is racemic mixture, is called as racemization, and the process of separation of racemic mixture into D or L form is called as resolution. So, here the racemic mixture is converted into enantiomers, that is optically inactive is converted into optically active. This process is called as resolution. Let us take another case. In a nucleophilic substitution reaction, which is shown here, X is replaced by Y. When you check the product and reactant, you find that the configuration of A, C, B is same as the configuration of C, A, B in the reactant. That means both the product and the reactant have same configuration around the stereo center, that is the carbon which is asymmetric here. So such type of reaction we can say that it proceeds with the retention of configuration. When we define this, we define in this way. If during a reaction the product formed has same configuration of the groups around the stereo center as of reactant, such type of reaction is said to be proceed with retention of configuration. Let us take another case. Here a nucleophilic substitution reaction is taking place, but when you compare this reactant and product, you can find that when OH, the nucleophile, is substituted, at the time the configuration gets changed. When you check the structures both, you can find that the position of R, which is here in the reactant, is now on this side. And the position of R2 is also changed. The position of H is also changed. That means during a reaction, when the configuration around the stereo center, when it get inverted, such case is called as the reaction proceed by inversion of reaction. For this, it will be very clearly understood when we take this case, that is in the figure as shown that umbrella is turned inside out in a strong wind. So similarly, the structure also get inverted as shown in the figure here. Such type of reaction we can say that it is proceed through inversion of configuration. Such type of inversion of configuration is also called as Walden inversion. Let's discuss inversion of configuration, racemization and retention of configuration through this picture. Here one example is taken, that is asymmetric molecule is taken, that is the central figure. In this figure you can find that the carbon is asymmetric, all the four groups are different. Now when the X is substituted by Y, it takes place in two ways. First let us find the root A. In the root 1, we find that the X is replaced by the Y. And when you check the reactant and the product, in this you can find that the position of, or we can say the configuration of ethyl group, methyl group, hydrogen does not change. It remains as it is. So such type of product we can call it as it is formed by retention of configuration. Let us check the root 2. In the root 2, when it takes place, it is observed that when the Y is replaced by X, we find that the configuration gets changed here. That means configuration of hydrogen, methyl is different from the case of reactant. So when you compare the reactant and product, we find that the configuration is changed, which is different from the reactant, and we can say such reaction proceed through inversion of configuration. And next is the root 3. In the root 3, when the reaction is taking place, that is a nucleophilic substitution is taking place in such a way that there will be a formation of both the product, then it is called as racemic mixture. That means the product B and product C both is formed. We can say the mixture of these is called as racemic mixture. This process is called as racemization. So in this we have compared what is inversion of configuration, what is racemization, and what is retention of configuration. Now let us apply this concept in SN1 and SN2 mechanism. In SN1 mechanism, the process takes place by racemization. That means in SN1 mechanism, the attack of nucleophile can take place with equal ease from both the phases. That is, the nucleophile can attack from this direction or from this direction. We can say it can attack from front and rear, forming a mixture of two enantiomer that is shown here. Such mixture which have equimolar mixture is called as racemic mixture. That means one will be dextrorotatory, other one will be levorotatory. So that mixture is called as racemic mixture is found. Because here the carbocation which is formed as an intermediate which is planar, so there will be two ways of attack of nucleophile, that is from the front and from the rear. So thus only we are getting the two product which is called as racemic mixture together. and racemic mixture is optically inactive. When we discuss about SN2 mechanism, in SN2 mechanism, inversion of configuration takes place. That means when the nucleophile attack, it results in the formation of a transition state, and because of this there will be the configuration get changed in the product, that is called as product is formed, that is inverted product. So we can say that in SN2 mechanism the reaction proceed through inversion of configuration. So from this we can conclude that in the SN1 mechanism, if the reaction takes place, that is optically active alkyl halide, the product formed is a racemic mixture which can be represented by plus minus sign, which is optically inactive. But in the case of SN2 mechanism, if the reaction of alkyl halide takes place due to the inversion of configuration. So let us summarize this video. In this video, we have discussed some of the important terms which we are using for the stereochemistry for the SN1 and SN2 mechanism, which are plane of polarized light. Next is asymmetric molecule having asymmetric carbon, which is optically active and chiral. Here we have discussed about some terms like racemization, resolution, retention of configuration, inversion of configuration. And by applying these all concepts, we concluded that in SN1 mechanism, the reaction takes place by racemization, but in SN2 reaction, the reaction proceeds by the inversion of configuration. So it is a quite important topic that we have discussed in this video. So all of you go through these points and note it out in your notebook. Thank you everyone.